All right, so hello everyone. Welcome to our talk on understanding the role of ontologies in knowledge graphs. My name is Kogan Shimizu. I'm a postdoctoral researcher at Kansas State University, but moving to Wright State University in just a couple of days, actually. My work really focuses on the ontology engineering and data integration aspects of the Nowhere graph. As I said a second ago, today's talk will center around how ontologies can be used in conjunction with knowledge graphs, and in particular, how they really improve them. So in order to make my case, so to speak, I've partitioned the talk into three main pieces. First, why you would want to use an ontology with a knowledge graph, or KG. I'll be using the acronym interchangeably. And that is, how do we use ontologies to integrate both data and knowledge? And incorporate their context, right? Then I speak a little bit about how we actually use ontologies for greater good within our particular KG, the Nowhere graph. And then finally, I'll introduce some of our ontology engineering tools and the design patterns that we have developed for the knowledge engineering efforts of KWG. So yeah, let's get started. All right, so in many use cases or scenarios or business applications and so on, the role of the knowledge graph is to integrate data. But there is so much lost if we simply take all of the data points and throw them into a bin. That's where the ontology comes in. It gives structure to the knowledge graph. We call this the schema, the same as you might find or might call in a relational database. Ontologies can be quite flexible, which is quite a boon. Many of the data sets that we want to integrate are heterogeneous in both format, which is a software engineering problem, and conceptualization, which is more of the knowledge engineering problem and really the focus of what we want to talk about today. So for example, consider the Nowhere graph, right? It integrates data sets across two main concepts, spatial or placial information and hazard information. It's easy to imagine that every data set, or nearly every data set, might have a different idea of what actually constitutes a hazard. Or they may not agree on where a specific event occurs or what it should be called, and so on. An ontology allows us to manage these differences in the data sets and come up with something that's actually integrated. In Nowhere Graph, we've successfully integrated over 30 different publicly available data sets, and this could not have been done as successfully as we've done so without an ontology to drive how each of the data sets fit together across an entire team of 14 odd people working on the ontology or the knowledge graph. We also want to focus on the use case scenarios, right? These scenarios are the drivers for the types of conceptualizations that we focus on, as well as the primary motivator when identifying the key notions in our data, right? Those central concepts that are important to understand and really drive how the knowledge graph is going to be used. We want to ensure that the graph and thus the schema are capable of representing the data and knowledge in a way that is familiar and, more importantly, actually useful to the people who are going to use the knowledge graph. Essentially, what this means is not all ways to organize or structure the data are created equally. Right? It's easy to imagine all of the data being present in the knowledge graph, but structured in such a way that the queries are overly complex or take too long to complete, effectively making the desired data to answer a question completely inaccessible, even though the data is there. An ontology is what allows us to examine rigorously and formally how the data should be formulated so that the queries are effective and are responded to in timely manner. So for example, we can consider direct relief, one of our project partners. They might use our graph to identify people, experts with a particular expertise or role within disaster relief, from perhaps evacuation strategy to post-disaster economic recovery, and then also use the graph to identify those places that need these experts most, right? So people with malaria competencies or malaria treatment competencies can be linked to the places where there's these sorts of endemics. As you can imagine, this is a particularly time-sensitive and critical task, right? The knowledge graph that incorporates all of these concepts together should be designed in such a way that it does not contribute additional stress to an already tense situation. So finally, then we have the competency questions, which are essentially the tests that we run in order to ensure that the knowledge graph and thus the ontology are meeting the needs of any users. And these tend to span multiple use cases or might even drive a single use case. And they tend to span multiple data sets. And so really these things allow us to understand how all of the data sets fit together, and then we can incorporate that back into the ontology. And so a couple of the ones that are really driving KnowWhereGraph, for example, span different levels of the metadata that's within inside of it, right? So you have the KnowWhereGraph talks about hazards, and we have data sets that talk about specific hazards, but we want to know what type of hazards are described in the KnowWhereGraph. By making sure that this competency question is a central focus, we can make sure that the schema or the ontology is designed in such a way that this question is answerable. And then the experts and the wildfires, these kind of pertain to the previous use case, and then that sort of hazard-driven data knowledge graph that we were talking about earlier. So onwards, so let's take a look at what the ontologies look like in principle, and then how it really interacts with KnowWhereGraph in general. So to build our ontology for the KnowWhereGraph, the schema for KnowWhereGraph, we use the methodology called modular ontology modeling, or MOMO. It is a well-documented, semi-iterative, 9-step process that generates an ontology that is comprised of interlocking modules. The modules generally comprise central components of the ontology. I called those key notions earlier, or the central components. These are things, the main drivers of conceptualization. These are the concepts that are most important to modeling the data, especially with regard to the competency questions and the use cases that we spoke of earlier. It was certainly stress tested in a interstate across the entire United States distributed execution, and almost purely virtual because we couldn't really meet up because of the circumstances of COVID-19. And then it was malleable even in the face of new team members and internships and all of these things that make working with the team pretty difficult, but it withstood the test of all of that. The first 3 steps, though, are pretty generic. They're essentially just scoping the use case, and so are the last 2, which is just produce the final thing. It's really the steps 4 through 7 that are the interesting ones. So modular ontology modeling is a pattern-based method, meaning that we attempt to reuse as much as possible these tiny self-contained models called ontology design patterns. These are abstract, domain invariant, best practice encapsulating ontologies, but they're tiny. They focus on a very specific thing that occurs over multiple domains. That's what I mean by domain invariant. And then because of that, though, that means we need to adapt them to the use case at hand. So for example, we can take a look at this very, very simple execution where we have to go from this abstract idea of a thing that performs a role for some time, that we would modify this so that it's actually an expert performing a job over some time, right? And this doesn't go completely into the execution, but this is a rough idea of how we call instantiating the patterns into something more concrete, more explicit, and more specific to the use case at hand. These yellow and blue boxes, these are called schema diagrams, and this is our other kind of secret ingredient with modular ontology modeling. This is where we focus on the graphical representation of what the schema looks like. We hide the logic for now because what we want to focus on is a broad overview, an intuitive overview of how all of the key notions are related to each other. And so that's what this graphical syntax is. And perhaps most importantly, though, it also gives us a structured way to approach that logical axiomatization. So we call this systematic axiomatization, but that's really just a fancy way of saying we go through each of the node edge node pairs within the schema diagram, and we attempt to logically formulate what that edge represents. In some former work or previous work, we've identified a list of 17 axioms that is just a logical representation of the meaning of that edge that cover the ways that two nodes in a schema diagram can be possibly related. And indeed, according to the study that we performed, the 17 axioms cover over some 90% of all axioms found in ontologies out in the wild. Um, However, the point is, instead of needing to understand the underlying logic, this allows us to describe a limited set of axioms using natural language. That means we can approach them without really exposing the logic at all. And then ask a domain expert if the two nodes in the schema diagram are related in this way. So is there always a temporal scope, a time period by which an expert must be performing their role, right? And either comes back yes or no, and so on. And then we can go through the entire schema diagram in this way, and then produce an axiomatization in little to no time or effort, and really not dealing with the logic at all. And then so the next step is to take all of these modules that we've produced and assemble them together. This is generally pretty easy because it just fits together like puzzle pieces. I call this metadata scaffolding, where you go from these conceptual components, these key conceptual components, and then you create these patterns or find the patterns that match to them. And then you create modules out of those patterns by instantiating them using that process that we did 2 slides ago, where we go from the more abstract concepts and models to the concrete models. And then you have the actual data inside of the knowledge graph called module instances. And you can see how you get the scaffolding of how the data is structured within the knowledge graph from this process, right? And so the idea of the modular ontology then is to produce these puzzle piece-esque models where you can interlock them, you can compose them in order to create this schema for the entire knowledge graph. These modules are important because they tend to bridge human conceptualization, right, and the data. For example, when I'm thinking of a new concept, or I'm trying to learn a new concept, I think of the more abstract case and I kind of narrow it down in my mind how this fits using existing knowledge and then the new knowledge and fitting it into my mental framework. And I want that analogous conceptual structure that I already understand, that would be the pattern, and then instantiate it into the module, right? Um, and so the modular ontology modeling aspect of this is to sort of bridge that human conceptualization, that analogy process to create these schemas quickly by composing these modules. But even more importantly than this is that the modules are built to be self-contained, just like the patterns, right? Which means if we have two modules that conceptualize the same notion but slightly differently, we should be able to replace one with the other without overly impacting the overall ontology. This could be viewed similarly to replacing puzzle pieces of the same shape. That's why this little piece of clip art is there. So the modules are puzzle pieces, and this is really helpful because if we need to change how a data set is provided to us, and we need to reflect this within the data, we can just re-instantiate the model from the original pattern and then replace in the existing schema with a new puzzle piece, right? So that's modular ontology modeling in a nutshell. So just a little bit about the KnowWhereGraph schema and why we really needed an ontology to do this in the first place. Because really, that's the entire point of the KnowWhereGraph, is to take all of these data sets that might have their tiny internal schemas that may or may not be documented, and then we want a singular artifact that integrates all of them so that we can answer those competency questions across all 30 plus data sets, right? We have 5 distinct pilots, or these use cases with varying consumer needs. And we want to conduct our spatial and placial integration and have a underlying discrete global hierarchical grid. And finally, we needed a way to sort of integrate all of the different types of formulations and conceptualizations of hazards across all of the different data sets. And so, of course, we turn to an ontology or a schema to make sure that all of these data sets can be integrated into a way that is communicable to the rest of the users instead of just blindly navigating through the graph. So this is what the schema looks like now, and it is probably completely unintelligible on your screens. It is on mine, and I have a pretty nice resolution. And I like to market this, I guess, as a way of saying that this is excellent because we have this incredibly useful and we have this incredibly robust schema, and by now it's grown so large that it doesn't fit onto a slide anymore. But the thing is, it's still quite useful. I could go over several slides, and you can take a look at these boxes. Which are the modules and how they interconnect with each other. But you can see how this is nice and organized, and this is the result of Shirley, who's sitting in the audience, her work to make this nice and intelligible. But these blue boxes here in the center are those primary conceptual components that all of these different data sets are integrated on. So this one here is a hazard, and hazard again is repeated here for cleanliness, but we also have the spatial features here and so on, right? This is how you can see this convergence into these top level components that allow us to interconnect all of these different data sets. And you can get from one data set to another by traversing through these pretty well-documented graph structures. And then, as I was saying earlier, there's no single formulation of what a hazard is and what it means to different organizations. And so one of the things that we're working on, Shirley and Mark in the audience, and then some input from myself and from some others as well, so don't I'm not trying to take credit here, is that we needed a way to describe what a hazard is, excuse me, if UNDRR, the United Nations Disaster, forgetting the other R, disaster relief and recovery, maybe. I specifically chose the icon without the words, and now I regret it. But essentially, if a data set publishes their ideas of hazards according to the UNDRR, we needed to make sure that there's a way that we can co-respond them to another data set that might talk about the same hazards, but is published according to the IRDR formulation of hazards. Right, and so what this hazard ontology is a generalization that allows us to integrate all of these different data sets along a single dimension, that hazard formulation. We would not be able to do this without an ontology to keep us essentially honest and consistent across all of the different data sets. And then on the other hand, this is the metadata model. So one of the things that you need to do when you're taking a look at the data inside of the KnowWhereGraph is you need to be able to trust where the data is coming from. And so now this is a step up on that metadata scaffolding. Part of the schema also describes itself, saying, where does this come from? Who wrote it? What data set is it about? All of these different things. You're missing in this particular diagram all of the namespaces and the overlaps with existing vocabularies like prov or void or voif and the Dublin core and SCOS. Like, these are all in here, but this is sort of the top level overview of the different relations and how they're there. All right. And so finally, we'll talk a little bit briefly about the sorts of tools and resources that we've put together for doing these sorts of schemas outside of KnowWhereGraph. So we have a spatially explicit design pattern library. We're slowly building this up. We have 2 in there, and then 1 new pattern that's not quite about spatial items, but is really useful in this use case. Commodity, which is a graphical design tool that produces schema diagrams with the underlying logical formalization, and the interactive knowledge browser, which is a way for navigating knowledge graphs using those schema diagrams as a first-class citizen. Kind of dig into those a little bit. So excuse me, we first have these the patterns. So we have a pattern, an ontology design pattern for depicting the causal relations between events. As you might imagine, events are extremely complex things, and nobody really agrees on what an event is. This was definitely a work in progress within our own team to try and come up with decent definitions for this. But what we wanted to do here is we wanted to link together how possibly non-spatially uh, corresponding or co-located events might impact each other or trigger each other or cause each other, right? Landslides might be caused indirectly by a uh, hard rains and a fire, right? And within the different isolated data sets, these relations don't exist. And so we would need to model them somehow according to that hazard ontology that says, hey, look, a uh, landslide was caused by the denaturing, the removal of all of the things that hold the dirt together, the roots and the trees, that was caused by a wildfire, burnt all those down, and then all of the water plus the loose soil became a mudslide, right? And so that's what this pattern is meant to do, is to say that a concrete event such as the Thomas Fire caused or resulted in the situation that would lead to the mudslide that caused an immense amount of damage in, I think, 2017. Next, we have a pattern for depicting the features of cells in a hierarchical grid. So this is really a way of saying there's a wildfire and it can be represented by this approximation of the so-called S2 cells, which are just these invisible grid that's laid across the entire globe. And they're hierarchical, so it's 4 cells to a supercell and so on and so on and so on until you have, I think, 6 cells or something for the entire world. And what we wanted to do is we wanted a way to encapsulate how the features in the tiniest cells can be summarized upwards into the hierarchical structure of the cells. And then finally, we have the pattern for aligning the vocabularies and taxonomies. This is something very new. It's actually under review right now. We submitted it last week. I don't know, time flies. And essentially what this allows us to do is to discuss or to formally state what the definitions and the relations between definitions of 2 different terms that might be called the same thing, but have different definitions. And so we wanted to formally and semantically describe the relation between these 2 things, and also describe how taxonomies correspond to each other and are modeled themselves. So it might be a subsumption, or it might have facets, and so on and so forth. It looks like I'm running a little bit out of time, so I'll hurry up. So this is Commodity. This is a pattern-based graphical ontology design and integrated development environment. And what it allows you to do is drag and drop these patterns that I talked to you directly onto a graphical canvas, and then you can double click on them and change the names of the cells, and it changes in the underlying ontology as well. So this is a plugin for Protege. Pretty neat, if I don't say so myself, because I am the primary author on this, and it does all of that module instantiation process that I discussed earlier just automatically for you. And then finally, we have the ink browser, or the interactive knowledge browser, which allows you to kind of take a look at the data within inside of the knowledge graph, but using the schema diagram as your primary vehicle of navigation. So this way you can take a look at what is connected to what, not in terms of explicit concrete pieces of data, but the entire classes of data that are related to each other. This is definitely a work in progress, and we're kind of need to work on the user interface, but this is a technology sort of demonstration. And that concludes my presentation for you with 18 seconds to spare. So thank you very much, and happy to answer any questions either now or asynchronously via email. Thank you. Shirley asked about 17 axioms that can relate about 90% of any two nodes. So this is a study.
I'll dig out the paper link, but you can talk about it.
Yes, so we have a paper, we call them axiom patterns, and they're essentially ways of describing the relation between them, and it might be functionality or existentiality or range and domain and subclass, and it's just really these very simple axioms. But because we're looking only between two axioms, there's a pretty limited number of ways that you can express these relations, and so the 17 axiom pattern list specifically covers about 90%, or covers a lot. And then it's not that it covers 90% of any two nodes, it's that the axiom patterns, if we go and we take a look at all of the existing ontology repositories that are out there, like OntoB or the OBO Foundry or the IOF, the Industrial Ontology Foundry, and take a look at the schema of SNOMED and stuff like this, all of the axioms, if we take them and we try and match them to these axiom patterns, about 90% of them are covered. I think it's a little bit higher, but I didn't want to overquote. All right, next question. How does one address the evolution of the schemas? Is there a support for versioning of the schemas? Also, are the queries aware of the schema versions such that if the version is asked is not available in alpha version, but may be available in the beta version of the schema? Ooh, that last one's a good idea. We do not support that one right there. Something to look into though, so I have to talk with Shirley about that. One addresses the evolution into the schemas. So OWL, which is how we author the schemas, has a standardized versioning system where when you publish the ontology, the namespace is created in such a way that the version is embedded within the IRI of the ontology. However, you can also consider when we create multiple mappings of the modules, where possible, we can use ontology alignment mapping language. I can't remember, it's called EODIM, I think. Pascal might remember, but essentially there's a way for creating these rules that correspond between complex alignments, which would be one mapping of a module to another that we can also encode. KnowWhereGraph is not yet at the point where we need to support these because we have simply evolved the schema, yes, but it's more of maintenance fixing where we do not want to support the backwards compatibility because it is wrong, right? We want it to be the correct, and if we support the sort of the versioning and the evolution, we want to go from one correct conceptualization to another correct conceptualization.
Cogan, I'd like to add that, I think that we are concerned about putting out ontologies with identifiers that some other group or even within our own graph is used, and then we realize it was wrong and we need to deprecate it. So if that happens, we then have to still maintain that IRI and make it clear that it's been deprecated and redirect it to the more formally correct version. So aside from the versioning, the inherent versioning capability that Al provides that Cogan described, at the individual term level, we also have a deprecation process.
Here's one from Christoph. How widely do we think that KWG patterns can be used in other graphs? So the patterns that we've developed here, so the three that I've kind of showcased here within the in the slide set, it is at least my opinion that these are general enough to be used outside of any KnowWhereGraph use case, as long as they kind of pertain to what the pattern's about, right? So any event related knowledge graph should and I believe could use these patterns for connecting the patterns together via the causal relationships. The pattern for depicting features of a cell in a hierarchical grid could definitely be used by anything that wants to represent, well, anything on a hierarchical grid system or the discrete global grid system. And then this last one is a little bit more niche because it's sort of metadata. Because what we're trying to do is to integrate the multiple taxonomies together, and I could see how this is useful outside of many use or in other many use cases, but it's definitely a bit harder to generalize because it fits a very specific need of integrating taxonomies together at the meta level. Last question, next question is, does the KWG support any languages such as Gremlin other than Sparkle? It does not. But that is not to say that Sparkle is the only way of interacting with the knowledge graph. We have a set of tools, and Christoph raised his hand, so maybe he has a better answer for me or than me.
No, I don't think that I have a better answer, but I thought that maybe it's good to say that Sparkle is the graph query language that we are using, but keep in mind that you can export into many other formats, right? You can export into JSON or GeoJSON directly from our interface. You can export into comma-separated value files or whatever, and then you can essentially do whatever you like, right? But when it comes to purely querying the graph, then what we are offering is Sparkle, or in fact GeoSparkle, and then API access, for instance, via faceted search, dereferencing, and stuff like this. But if you have specific use cases that would need something else, then speak up and we can see what could be done there.
Hi, everyone. Can you hear me?
Yes.
Yes, very well.
Yes, thanks for your answer. So I was exploring a couple of other graph databases, so I was not quite sure like which, if you all, if the KHub, the knowledge graph currently supports any other query languages like the Gremlin, which is supported by the Tinkerpop. So, and what is the compatibility with like other engines such as the Neo4j and things like that. So just newbie to the graph world. So
I just I had to refamiliarize myself with Gremlin a little bit. So Gremlin, I believe, works with Neo4j and a couple others, and it also works with Amazon Neptune. And so one of the things that is really powering KnowWhereGraph, I said earlier that KnowWhereGraph is focused on this spatial and placial integration across data sets. And in order to power this, we use GeoSparkle. And the OGC standards for representing space coordinates, right? So the geometries and the spatial features in these things. And Amazon Neptune, which supports Gremlin, does not support that spatial integration system from GeoSparkle. And so of the two, it is way more important for us to make sure that we have that GeoSparkle and that topological integration aspects for KnowWhereGraph than it is for us to support alternate query languages. With Neo4j, you get a little bit into different ways of formulating what a graph looks like. And so Neo4j, if I recall correctly, creates these property graphs where you can use node, like triples can be the head of another triple somewhere else. And one of the problems that we have with that is that also Neo4j is not currently possible right now to express a rigorous schema in the same way that we have expressed one over an OWL knowledge graph. And I see Pascal has a raised hand here, so defer to him.
You know, just wanted to add. So there's actually some nice preliminary work coming out of the Amazon Neptune team on property graphs and RDF. I'm not really familiar with property graphs too much, but from the bit I've read in particular, also from their comparisons and efforts of coming up with a generalized language over both, there are restrictions on what property graphs are, which to my understanding, I haven't done an exact analysis. There's some complicated stuff which are just tricky to do in property graphs. So from that perspective, RDF is still more powerful. But property graphs are sometimes just the kind of preferred usage for something simple, but we don't have anything simple here. And that also goes in the same direction what Cogan mentioned, like, for example, GeoSparkle support, which is just so central for all the spatial stuff. And a lot of triple stores just don't have it, right? So that's another thing. So hopefully there will be, all right, Olaf Hartig did some work on that as well. Yes, correct. So so I think that's the general tenet, and we're very happy with RDF from that perspective, and hopefully these things will merge at some stage anyway. So I think it's great what the Amazon Neptune people are up to here. You may want to look up Ora da Silla. I believe there's something on Archive on a comparison. This was really a very nice read for me, kind of explaining the differences and so on. I'll post it in the chat as soon as my system is quick enough for that.
Well, while we have a little bit of a radio silence, Pascal, I really like what you said, and maybe for those listening, it would be also interesting if you could say something about your thoughts on whether this really matters, the RDF versus labeled property graph discussions and stuff like this for something like an open knowledge network, or whether the paradigm, so to speak, how things should be designed matters more.
So there's two different things here, right? It is a misconception, right? Which is sometimes heard is you just use whatever RDF Sparkle property graphs and you make semantic integration of data easier. That's just not the case. You need to wield them wisely. So when Cogan showed, for example, the schema, he showed it in a format which just, well, it's essentially a visual format for us people to look at and to kind of understand the gist of it. Although underlying of this, of course, is a full-blown ontology with ontology axioms and so on. But both levels are important. There's the conceptual level, which is important, and then the conceptual level, which is just a diagram. But then it's also important, what do the things in the diagram mean exactly? And this you can do using, for example, a formal axiomatization in OWL, for example, if you want, or something else. Well, and then here's the problem, OWL or something else, right? And then on the graph structure, you can say, well, okay, now once we have a good schema, which you really need for this flexibility and ability to growth and not get lost in the weeds, then what graph languages can we use for expressing this graph? And then we go into kind of what do we want to use there. The really key important thing for semantic interoperability is having a good schema which really resonates with the data, is modular and is extendable. That's the key thing there. But then, of course, which exact languages you use to express these things is extremely important as well, simply because it locks you into certain choices sometimes, like, for example, property graphs are not as flexible as RDF, or it locks you into using specific tools. And in that case, you add another difficulty layer when you try to, for example, try to reconcile graphs which are on these different paradigms. So in the end, I think one probably should settle on some general approaches, both to graph design and schema design, and to having at least a base compatibility with, well, one existing standard. And RDF is the more flexible one, so I'd go there. So I think it matters, but the conceptual layer should not be forgotten, because if you just use RDF and OWL and then do what you want and don't heed much to conceptual concerns, then in the end, you will not make things easier to reuse. And a typical example of that would be the linked data cloud, which is actually a large integrated knowledge graph, if you want to put it like that, but it's just all over the place and there is no common governance. And there is just no reasonable way of developing federated queries over the whole knowledge graph because it's in other words, it's a mess, right? It's helpful for a lot of things, but it's also completely hopeless for other things, in particular for more intricate stuff.
Yeah, sorry, Mark. So I have a question here. I agree that conceptual model is also important here, and the design pattern or ontology design pattern play roles here. But to me, like how to design, design pattern is a pattern, and we want it to be reusable and extensible. So it to me like more like a philosophical question. Like we want to find a balance between generality or generality and speciality. So do you have any guidance, or can you comment on how to find such a balance? How do you evaluate whether a pattern is really useful or extensible? How to find that kind of balance in between? Can you comment on that?
Finding the balance is pretty tricky, and what we did with KnowWhereGraph is maybe not the most effective way at finding the balance, because we started with a single use case in mind, and then we needed to make some effort to contrive different examples to drive the generality. And so because we started with a particularly scoped vision, when we needed to go upwards to find further examples, this is a bit of a problem. So generally, what we've done to make patterns in the past is we get multiple domain experts, not just one with a particular focus in mind, but multiple, and then ask them what is common and get them to kind of roughly agree on certain things. And then eventually we iterate through enough diagrams that we get something that's sufficiently general across multiple multiple use cases.